All right, I'm going to take you through a few oxidation and reduction practice questions. So hopefully it'll make a little bit more sense. Are you ready?
All right, write the oxidation number for each element in the compound. Here's my list of elements. So I need to write an equation. I need to look at how many of each element are in this formula. So I have 1K plus 1 Mn, which is manganese, plus I have 2 oxygens. Sometimes when I have an O, I like to write it like that so I don't confuse it with a 0. Now I need to set it to equal to something or it's not an equation. So look up here. Do you see a charge? No, you do not. So this equals 0. When would it not equal 0? Look at this example. SO4 2 minus. See this? So it would not equal 0. What would it equal? S plus 4 O's would equal -2. What about this one? NH4 plus. Well, see this? So that would be 1N plus 4 H's equals +1. Since there was no number, it's +1. Okay, so that's just what to do if there is a charge. But you see, no charge, so I set it equal to 0. Now I go to the periodic table and I start looking them up. Oxidation number for K, easy peasy, +1. Oxidation number for Mn, giant list. O, 2 negative. So here I already know K +1, O -2. Plug them in. +1 plus Mn plus 2 times -2 equals 0. Multiply that out. -4. Combine like terms. Add 3 to both sides. Notice how I write the plus. I don't just write 3. And then I can put this here. And it works. And quick math, ready to check. K is +1, Mn is +3, and O is -2. But there are 2 O's, so that's -4. So I have +4 and -4. Brilliant. That's it. All right, I'm going to do this question right here. Write the oxidation half reaction. So that I don't forget, I'm going to do this very quickly. Make a very quick number line. Going this way, Leo, or oil. Going this way, Gur, or rig. Now write the oxidation half reaction. So let's look. Copper starts at 0. This Ag is +1 because it's literally written there. This copper is +2 because it's literally written there. And this Ag, since it's just an element in its elemental form, is 0. So copper went from 0 to +2, and Ag went from +1 to 0. So let's look. Copper went from 0 to +2. Ag went from +1 to 0. All right. So this arrow right here for copper from 0 to +2 is following this arrow. So that is Leo. And Ag going from +1 to 0 going this way and following the Gur arrow. The Leo arrow is oxidation and the Gur arrow is reduction. So let's write, which one are we doing? Oxidation. Okay, so let's write the oxidation. We have Cu, which is what we started with. On the other side, it's Cu2 plus. Now our last step is to make sure charge is balanced. Well, this side, so here's our divider. This side has a charge of 0. This side has a charge of +2. That is not possible. I cannot leave it like that, so please fix it. So how do I fix it? I have to add the electrons where they belong because redox involves moving electrons. So put the electrons where they belong. So copper went this way. Again, that's Leo, losing electrons. Do you see how the arrow points this way? That says, hey, yo, put the electrons on that side. Okay. How many electrons? Well, how many spaces did it move on the number line? 2. So plus 2 electrons. So now what's the charge on this side? Well, that's a positive 2. That's a negative 2. And a positive 2 and a negative 2 equals 0. So both sides do have the same charge, 0 and 0. And that's it, okay? This right here is the oxidation half reaction. This is the substance that was oxidized. This is the substance that we call the reducing agent. Just to review that. Okay, now I'm going to do this question right here, but I had already done all of this work because before I had written the oxidation half reaction. So now I'm going to write the reduction half reaction. But I'm not going to rewrite this whole thing. Like, come on now. Don't make it harder for yourself. So I'm just going to look at Ag this time because I'm looking for reduction, and Gur is reduction. So Ag changed from Ag with a +1, and on the other side of the equation, it was Ag with no charge. So like that. Okay. Let's check and see the charges of both sides. So this side has a +1, this side has a charge of 0. Is that correct? Is that balanced in terms of charge? Nope, 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 nope. Okay, so that's as Ducky would say in Land Before Time. So what do I do to fix it? I put electrons somewhere. Okay, I can only put electrons because those are the things that are moving around in redox. And look back at the number line. See how the arrow for Gur points this way? It says, hey, yo, when it's reduction, please put the electrons on that side, over here. So how many spaces on the number line did it move? 1. So I'm going to just put 1 electron. I don't have to put the 1 in front, but I can. So let's check charge. That's -1, that's +1, that's 0. Beautiful. I have 0 on both sides. There is the reduction half reaction, which means this is what is reduced, or the oxidizing agent. Okay? Okay, for this one I need to build the redox reaction. So redox, okay, is reduction plus oxidation. All right, so what was my reduction reaction? So let's go back. Here was reduction. It was an electron plus Ag positive yields Ag. And our oxidation half reaction was copper yields copper 2 plus 2 electrons. All right, now when we do redox, we combine them together and smush them back together and make one reaction. But one last thing to check. Look at the electrons. How many electrons are in this side that are being gained? Well, that's 1. How many on this side being lost? 2. Well, that is impossible. I have to make them equal. I have to have the same number of electrons being lost and gained. The number of electrons lost must equal the number of electrons gained. So how do I do that? Well, I don't want to cut this in half because I can't cut this copper in half. So what I want to do is take this whole entire equation and multiply it by 2. So I will get 2 electrons plus 2 Ag plus yields 2 Ag. My reduction is going to be the same. We're going to check and make sure it works. Oops. 2 Cu2 plus 2 electrons. Okay. So does matter balance? 1 copper, 1 copper. 2 Ags, 2 Ags. Yes, matter balances. Do electrons balance? 2 on this side, 2 on this side. Beautiful. Now I can combine them. So when I do that, I get 2 electrons plus 2Ag plus. And then see how this is on that side? Plus Cu. Yields on the other side. 2Ag, and then what's on the other side here? Plus Cu2 plus 2 electrons. And this is the redox reaction built from the reduction and the oxidation. Now the order of things on this side doesn't matter as long as these three things are on this side of the arrow, and the order of these three things doesn't matter as long as these three things are on this side of the arrow. Okay? Okay, let's look at this question. Base your answer on the following redox reaction which occurs spontaneously. What does spontaneously mean? On its own. Means I don't have to do anything to it. It just plain old happens. Okay? So now it says state what happens to the number of protons and electrons in the zinc atom when it changes to Zn plus 2 as the redox reaction occurs. Whoa, so wordy. Okay, so let's look here. 0, 1, 2, -1, -2. This way is Leo. This way is Ger. Okay. What is happening to zinc? So we're only looking at zinc right here. So zinc is going from Zn to Zn2 plus. So 0 to 2 plus. This is Leo, right? That's oxidation. Le, that means loses electrons. So what happens? The number of electrons decreases because the Zn atom loses 2 electrons. And then, but it also says, what about the number of protons? The number of protons stays the same. Protons and neutrons don't change. Just the electrons. Just the valence electrons get moved around. Protons don't change. Neutrons don't change. Okay? All right, now we're looking at this question, which is the anode, which is the cathode. An important piece is that this occurs spontaneously. We also know that by looking that it's a voltaic cell. Another way to say voltaic is galvanic. This thing is literally a battery. Okay? So how do I determine what's the cathode and what's the anode? Well, I need to look at table J. So table J is the activity series. The most active metals are at the top. That means they will be oxidized because metals are really good losers. Okay, they lose electrons. So what I have to do is find my two metals, zinc and copper. And I look for which one is higher on the table, which one is higher of those two. Well, zinc. That means zinc will be oxidized because in this type of electrochemical cell where it happens spontaneously, the higher one is always oxidized, the lower one is reduced. Okay? Now, something else to notice, salt bridge, right, that allows ions, right, to flow back and forth. The wire, electrons move through the wire. All right, so let's get back to identifying cathode versus anode. You should remember this phrase. Now, I'm not going to attempt to draw an ox or a red cat, but anode is where oxidation occurs and reduction occurs at the cathode. So which one had reduction? That was copper, so that is the cathode, which, like cations, would be positive. And the zinc electrode would be the anode, because anox, and it would be negative. So that means over time what will happen is this piece of metal will lose electrons and get smaller and smaller and smaller and smaller and smaller. And this electrode, the copper side, will gain electrons to get bigger and bigger and bigger. So what happens, this piece of metal gets smaller and smaller and smaller, and when it's all gone, the battery dies. It runs out. Okay? So that's it. That's how it works. Okay, which direction do electrons flow? Well, remember we said this was the reduction side, that was the oxidation side. So this was anode and this is cathode. That's all you need to know, because the rule is electrons flow from the anode to the cathode. So the electrons flow from anode to cathode. So in this case, it would go from Zn to Cu. It would go like this. When it asks you for a direction, please do not say left, right, up, down. Say this, from anode to cathode, or from the piece of metal that's the anode to the piece of metal that's the cathode. Okay, what is the purpose of the salt bridge? The salt bridge allows ions to flow back and forth, or another way to say it is it keeps the cell neutral, keeps the charge neutral. Okay? The wire is for the electrons. The salt bridge is for the ions. Okay, so I'm going to start from scratch for this one. It says draw an electrolytic cell, and my two metal choices are Mn and Sr. Okay, so when I have an electrolytic cell, okay, what I need to have in the electrolytic cell is I need to have two pieces of metal. Okay, so let's just do this. Let's put our two pieces of metal. Those are our two electrodes. Okay, I need to have those two pieces of metal connected by a wire, and then I need to have a battery. Okay, so that's the symbol for a battery. I could have drawn an actual battery like this. Okay, but there's the battery. All right, so we're not going to use that. I have my two pieces of metal connected, right? I have an electrolyte, so that's this liquid. And in an electrolytic cell, the electrolyte is for ions to flow around. Okay, so I have two pieces of metal. I have this piece of metal and I have this piece of metal. Okay, now I have Mn and I have Sr. Okay, so which is which? Well, let's look at table J. Where's Mn? Right here. Where's Sr? Up here. Okay, so normally what happens is Sr would be the oxidized, and that would be the anode, right? Anox. Well, this battery right here is like, you are going to swap places. So this was supposed to be the anode, but the battery is like, you switch places. So this Sr is going to be the cathode, and this Mn is going to be the anode. And then because this Sr was originally supposed to be the anode, this cathode is actually negative, and this anode is positive. And that's the big switch in an electrolytic cell. You have a battery, and the higher metal is actually the one that is the cathode, which goes through reduction, and this one goes through oxidation. But pretty much everything else is the same. So the electrons go through the wire from anode to cathode. This piece of metal gets smaller and smaller and smaller. This piece of metal gets bigger and bigger and bigger. Ions flow through the electrolyte. Okay. There you have it. This is an electrolytic cell. Okay, so now we're going to do the same thing, but this time we're going to draw a voltaic or a galvanic cell, and we're going to use the same exact two metals. So we're going to use Mn and Sr. This time, here's where they are. Sr is higher, so it is oxidized, and Mn is reduced. Okay, that's normal rules. So how does it usually look? I usually have like two beakers, right? I have liquid, that's the electrolyte. Okay, I have a salt bridge that is going to allow ions to flow back and forth inside the salt bridge. Okay, I have a piece of metal over here, that's the electrode. Piece of metal over here. They are connected by a wire. Sometimes you will see a voltmeter or a light bulb. Okay, so I have two pieces of metal. Inside here is the electrolyte, right? But since these two containers are separated, we need the salt bridge so that the ions can flow back and forth. Once in a while, just so that you know, sometimes you'll see like one big container, but it will be separated like this by porous material instead of a salt bridge. So what that means is the ions could flow back and forth this way, but you would still need the other pieces. Electrode over here, connected by a wire, most likely to a voltmeter, okay? This would be the electrolyte. All right, so it can be like this, but I'm going to focus on this one. All right, so we have two pieces. We have Mn and we have Sr. We already determined since Sr was higher, it was oxidized. Mn, since it was lower, it was reduced, because this is just a voltmeter, right? So things behave like they should. So this is anode because it's oxidation, anox. Red cat. Anode is negative, like an anion. Cathode is positive, like a cation. The electrons flow through the wire from anode to cathode. Okay. As the electrons are flowing this way, this piece of metal gets smaller and smaller and smaller and smaller. And this piece of metal gets bigger and bigger and bigger. So then when this piece of metal runs out, this battery no longer works. Okay, so that is an electrochemical cell called a voltaic cell.
And that was some redox, some oxidation and reduction practice. I hope that helped a little bit.